Hello everyone, welcome to the numerical methods course, and from this section we are going to learn about numerical integration. And numerically we use different methods to find out the integration of a function or polynomial or tabulated data. And first of all we are going to learn about the basics of numerical integration, and then we are going to dive into the details of trapezoidal rule, one of the most widely used methods for finding the numerical integration. So first of all, let's look at what a numerical integration looks like. If you remember, this is the definite integral mathematical formulation. The f of x is the integration function, dx is the integral variable, and that's why we have used the dx term. A and b, these are the lower limits and upper limits of the integration, and I is the integration value. So let's look at the graphical representation of this integration function. We have drawn the function within this graph. Along the x-axis we have the x variable, and along the y-axis we have the function f of x. So we have the limits. Lower limit is a and the upper limit is b, and we have to calculate the area. If we calculate the area under these curve within these boundary a and b, then these denotes the integration of the function. Okay, so that is the definition of a function, an integration of a function, if you want to visualize it from the perspective of numerical methods. So okay, so we have to calculate the area under this curve within this boundary, and then we will actually get the numerical integration. So we segment this shaded portion into smaller parts. Okay, what we can numerically do, since we do not use the analytical approaches here, then we have to use some approaches that approximately calculates the area of the shaded area. So what we do, we segment the shaded area into smaller parts. That means smaller geometrical parts. We do the geometrical parts because we can easily calculate the area of individual parts easily. That's why we are using the geometrical parts. We are not using randomly selected parts, because that would be very much tough for you to calculate the area of a random part. So that's why we use the geometrical shapes. Okay, so we are going to segment the shaded area into some smaller geometrical shapes, and then we are going to find out the area of each segment and sum over all the segments. As a result, we will get the total integration under this curve. That means we are going to find out the total area under this curve. So there are various approaches that we can follow to find out this area. We can actually segment the whole integration plane into smaller square segments. For example, in this figure, we are segmenting the area under the curve into smaller square parts. Okay, so what we can do, we can find out the area of a single square, and then multiply that area by the number of squares that are under this curve. Okay, so there will be at almost 1 2 3 4 5 6 1 2 3 4 5 6 7, so almost 42 to 43 segments under this curve within this boundary a to b. So we are going to find out the area of a single square and multiply with the number of the squares under this curve within this boundary, and that's how we can calculate the area. That's one approach actually, but physically we do not follow this approach, because in this way we have to calculate we have to segment the portion of the curve under this curve into a lot of square segments, and that's not feasible actually. So what we do, this is a square segment, so we are going to follow the vertical segments. That's why in this section, in this figure, we are going to segment the area under the curve into smaller vertical segments. As a result, each of these segments are of similar width, but they have different heights. Okay, they are of similar widths but they have different heights. So these are the rectangular vertical segments. So we can also follow the trapezoidal vertical segments or rectangular vertical segments or triangular vertical segments, but most of the time we use the trapezoidal or rectangular vertical segments. So if you look at this figure, you see there are some portions of these vertical segments that are not under this curve. They are above the curve, so that is not included into the actual integration value. So that's how these arrow terms are included into the numerical methods of integration. These over segmented curve which are beyond the curve, these segments are actually the error of these methods. So whether we apply the trapezoidal rule, or whether we apply the trapezoidal segments or vertical rectangular segments, we will have these areas which actually include the error. So we are going to find out the one application that is being used for applying the in numerical integration. For example, we have these data. These are not continuous data, these are discrete data points. For example, at I equal to 1, y has a specific value. For I equal to 2, y has another specific values. So these are discrete data points. So if I want to calculate the mean, what we do, we sum over all the y values and divide it by the number of data points. So this is the mean when we want to calculate the average of a discrete data points. So what about continuous data points? If I have a function f of x which continuously varies over x, that means at each point of x I have a value of y. In the case of discrete data points, we did not have any value within these data points, two discrete data points. So these were discrete, but this is continuous. So to find out the continuous value, a continuous mean value of a continuous function, we have to use the integration. That means we are going to find out the area under the curve within this boundary and then divide it by the width of the base. That means b minus a. Okay, the width of the base is b minus a. Here the width of the base was the number of segments, but here in continuous data the width is calculated numerically b minus a, because we have continuous variables. Okay, so that's one application of numerical integration. So there are two approaches that we can follow for calculating the numerical integration. One approach is closed methods and another approach is open methods. We are going to find out the difference between these methods, but let's first find out some of the methods that are being used under both of these categories. Under the closed methods, the closed method actually denotes that we do know the function values at the ends of the limits of the integration. So we will graphically look at the definition here, but right now we are going to find out some of the methods like trapezoidal rules or Simpson's 1/3 rule or Simpson's 3/8 rule. These methods are being used to find out the numerical integration whenever the function values at the end of the limits are known. So these are known as closed methods. So these are also in a sense also called Newton-Cotes formula, and they are frequently used for calculating the numerical integration of tabulated data. Okay, there are some other approach which is known as the open methods. Under this category we do not know the function values at the ends of the limits. Okay, that's the difference between the closed methods and open methods. So these open methods are usually used for solving differential equations, and they are not familiar with the normal approaches. And also we do use some other methods to calculate the integration of functions and equations. So these closed methods are used for tabulated data, and these open methods are used for solving differential equations. But to find out the integration of function and equations, we have to move for other special methods like Romberg integration or adaptive quadrature method or Gauss quadrature method. So these methods are used for functions and equations. So let's see what is the difference between open methods and closed methods. In closed methods, we do know the function values at the end of the limits. Look at this figure. We have the limits here a and b. A is the lower limit and b is the upper limit. So, and also we know the function values at these limits. Okay, we have the function value here by the black dot. Also, we have the function value at the upper limit at this black dot. So whenever we are talking about the closed method, we actually know the function values at these limits. Okay, But in open methods, we do not know the function values at the limits. Look at this here, the limits are a and b, but we do not know the function values here. Okay, that's the difference between open methods and closed methods. So first of all, let's look at the Newton course methods, that means the closed methods. The integral can be used, can be approximated by using a series of polynomials, and those polynomials are being applied piecewise to the function at different segments. So what does this mean actually? Well, we have a, say for example, we have a function here which is drawn here in this figure, and where the limits are a and b, and we are going to segment this portion under this curve within this boundary into smaller segments. Each of the segment, say for example, we have 3 segments here, and each of these segments have similar width, although they have various height, that means they have different heights, but they have similar widths. So that's the basic theme of Newton course methods. So what we are going to do, we are going to find out the area of each of these segments and sum over all of these areas and get the total integration area and as well as the integration value. So these segments are different heights. So we can approximate the what we can do, we can approximate any is one kind of polynomial equation to find out the area of each segment, and those polynomials can be of first order, that means linear, or second order, that means quadratic, or higher order. So these polynomials are the basics of Newton course formula. We get a polynomial of each segment. Okay, so there are 3 segments here. These are the end segments, and the middle one is the middle segment. So let's first find out the first method that is so frequently used under the closed methods, which is named as the trapezoidal rule. The trapezoidal rule comes from the fact that we divide the area under the curve into smaller trapezoidal segments. So look at this figure. In the figure we have a function, and we have to calculate the area under this curve, that means the integration, and that's why we since it is a closed method and it's Newton course formula, one of the Newton course formula, that's why we segment each of these segments are separate trapezoids. Okay, so this one is the one trapezoid, this is another trapezoid, this is another trapezoid. So these are separate trapezoids. So we can easily calculate the area of each of these trapezoids and then sum over all of these segments. So that's why it is known as the trapezoidal rule, because the segmented portions are of the geometrical shape like trapezoids. Okay, so if they were of a rectangular shape, I don't know, we might have called those as rectangular rule or something like that. But right now we are using the trapezoidal rule because it is the most basic one. So let's say we have a function that we want to segment into n smaller segments. So these are the limits a and b, and we want to segment this portion of the under the curve into n smaller segments. Okay, so what is the width of each segment? We can easily calculate the width of each segment by this formula. The difference between the upper limit and the lower limit, b minus a, divided by the total number of segments. So that calculates the width of the each segment, which is denoted as h. Okay, now we want to calculate the area of the first trapezoid. So we already know the area formula for calculating the area of a trapezoid, which is something like this: half times the width of the trapezoid, which is h, times the summation of the function values and of the parallel segments. Okay, this trapezoid has 2 parallel lines, which is at a and x1. So these are the 2 parallel lines. So we want to calculate the function values at these 2 vertical lines, that means f of a and f of x1, which is this one. So this is the summation of the parallel lines of a trapezoid. and h is the width of that segment, and we have a multiplicative factor of half. So that's the area of the first trapezoid segment. Similarly, we can calculate the area of the second trapezoid, which can be something like this: half times the area, half times the width of the segment, that is h. Since all of these segments are of similar width, that's why we have a common factor here, h, and we have to sum the function values at these two boundaries. So we have this x1 can be denoted as a plus h, that's why we have this function value f of a plus h, and x2 can be denoted as a plus 2ish, that means the function value is f of a plus 2ish. So that's the area of the second trapezoid. We can easily simplify this formula, which is f of x1 times plus f of x2. So that's the area of the second trapezoid, and this is the area of the first trapezoid. So that's how we can calculate the area of each of these segments and then sum over all of these areas. So the total area should be the sum of all the areas of all these trapezoids, a1 plus a2 plus a3 up to an. So this is the total area under this curve within the boundary. So if we sum over all of these area terms, this is the area of the first trapezoid, and this is the second trapezoid, this is the area of third trapezoid, the n-1th trapezoid, and this is the area of nth trapezoid. So these are the areas of all of these smaller segments. So if we just collect similar terms, so we can get the final form something like this. We have two terms here. The first term denotes the area of the first and the last segment, and the second term denotes the area of all of the middle segments. Okay, so the first term denotes the area of the first and last segment. So both of these terms are actually similar, but the middle segments has an extra multiplicative factor, which is 2. Okay, so that's the difference between two different type of segments. The first and the last segment has this form, and the middle segments have this form. So we can further simplify this formula mathematically, which can be denoted something like this: h divided by 2, which is the common factor which is present in all of these segments. The first and the last segment are f of x0 and f of xn, and the middle segments are these 2 times f of x, sum over all these middle segments. So this is the final form, the numerical trapezoidal formula for finding out the integration of a tabulated data or function or integration equation. So what we can do here, if we increase the value of h, this h denotes the width of each segment. So if we increase the value of h, we are actually decreasing the accuracy. Okay, we are actually increasing the accuracy, because as we decrease the size of h, that means each of the segment will have smaller widths. Okay, we will have smaller widths and the better approximation of the area under this curve. So we will have lots of smaller segments whenever we decrease the value of h. Okay, so decreasing h increases accuracy, but it also increases the computational cost. Why? Because we will have more segments and we have to calculate the area of more trapezoids. So that's the trade-off you have to make. You cannot just decrease the value of h arbitrarily, because that would cost you a lot of computational time and memory. Okay, let's look at some of the examples about the effect of h. Look at this. We have only just 2 segments. This is a function, and this is a curve, actually curve of a function f of x, and we have only 2 segments. And if we just want to calculate the area, we will have these 2 segments. Okay, if we just increase the number of segments, that means decreasing h. This is for n equal to 3, n equal to 4, and n equal to 5. So look at this. As we increase the value of n, that means as we increase the number of segments and decrease the value of h, the accuracy increases. Okay, this last figure actually calculates the integration or the area under the curve more precisely than these 3 ones. Okay, so look at this curve has some of the portion. Look at these white portions under this curve, these are not included in the area. So in this curve, these white portions are not included in the area. So as we increase the value of n, that means increase the number of segments, the area of the white segments decreases. That means we can cover most of the areas under the curve. Okay, that's the theme. Actually, we can increase h, and that's why we can decrease the accuracy, but decreasing h we can increase the accuracy. Okay, so let's look at an example here. We have a function f of x is this, and we have to estimate the integral of this function from a equal to 0 to b equal to 0.8. So these are the limits. The lower limit is 0 and the upper limit is 0.8, and we have to use two segment trapezoidal rule. How we are going to do that? We have to calculate the width of each of the segments under the curve. Since we have already been told that the number of segments should be 2, that means n equal to 2, so we can easily calculate the value h, which is b minus a divided by n, which is 0.4. So the first segment should be from 0 to 0.4, and the second segment should be from 0.4 to 0.8. Okay, so we calculate the function values at each of these boundaries, f of 0, f of 0.4 and f of 0.8. okay, so what we can do now, we can apply the trapezoidal formula in direct way, and we can find out the value of the integration, which is 1.0688. okay, we have already given the value of the correct integral, which is 1.640533. This was analytically calculated, so that means this was exact value of the integration, but we have found a value which is 1.0688. so that's why we have found an error, the true error percentage, which is 34.9%. so that's a big error. So how can we decrease this error? We can easily increase the number of n. That means we can easily increase the number of segments. As a result, the value of h should decrease, and the value of I should have a value which is closer to the this value, this true value 1.640533. so that's how we can decrease the error. So that's the end of this slide. In this lesson we have learned about the basics of Newton course formula, and we have find out the basic of and first formula, which is known as the trapezoidal rule. This is a special type of Newton course formula because this is frequently used in numerical methods, and we have seen an example which is used to calculate the trapezoidal rule, which has been used to calculate the integral value and using the trapezoidal rule. So I have already attached the MATLAB code of these trapezoidal rules, so please go through the details of the MATLAB course and find out how this method can be implemented computationally. So in the next lesson, so we are going to learn about the Simpson's rules, which is an advanced algorithm under the Newton course formula and the closed methods category. So till then, thank you so much.